So we talk about the inner product of tensors. Now, the product of or the process whereby we combine the outer product and the contraction of tensors to produce a new tensor is what we call the inner product of tensors. So consider, for example, two tensors Aijk and Bpqrs. Then the inner product of these tensors can be expressed as Cijqrs, which is the process whereby we combine the contraction. Contraction basically reduces the order of the tensor by 2, as we had seen in the previous lesson. For the outer multiplication, we would have just combined these two to form Ijp Cqrs. We would have combined to form a tensor of order 3 plus 4, which is 7. But when we apply the contraction, it reduces the order by 2, so we end up with a tensor of order 5, or the tensor of rank 5. Next, we look at the quotient law. The quotient law is an indirect method of checking whether a set of functions forms components of a tensor. The law basically states that if there are nt functions of coordinates xi forming the components of a tensor of order r, then the inner product of these functions with an arbitrary tensor is itself a tensor. And we can consider an example where if we have a set of n3 functions, a, I, j, k, these functions will form components of a tensor of the type that is indicated by these indices, provided so we have ai, if br ij is an arbitrary tensor, and then we have this product giving the inner product giving crk. So provided that brij is an arbitrary tensor and crk is also a tensor, then ajk will form the components of a tensor of rank 3. We can have this expression in a new coordinate system xi bar, and this equation 1.21 can be expressed in this form. Here we just changed the coordinate system. Now, if we use equation 20, that's where we defined the components of a mixed tensor of order s plus p. Then we can write this equation 1.22 this form, where we have C Lm. This one transforms according to this equation here. Remember when we write C bar Rk, this one should transform to C. This should transform to C Lm according to the equation x bar r by partial xl partial x bar k by partial xm, which is what we have here. Then, of course, bst b bar r I j. Sorry, we have ij will transform to b u st according to the equation dx bar r by dxu times the partial derivative of xs by x by I ds, sorry, not s, but xt by dx by j. This is what we have here, which is what we have here. So when we substitute there, we equate those two, and then if we substitute equation 1.21 into 1.23, 121 is this one. We substitute into the equation that we have obtained here, then we change the indices. We change the indices using this equation now. Then we end up with this equation. Now, from here we can bring this term to this other side. We just move this term to here so that we have this equation. And we see that dxr by dxl, we factor out some component here, this one. Then we end up with this equation from which this quantity here, if we multiply both sides by dx alpha by dxr and a summing over r, we end up with the equation 1.25. And because BLST was an arbitrary tensor, then the quantity inside the brackets must be 0, from which we can rearrange. If we equate this to 0, then we can take one term to the other side. We end up with the equation 126. And in a multiplication with this quantity here will give us this expression, so that ASTM is a tensor of that order having all contravariant indices. Now we look at the conjugate tensor. The covariant tensor Aij and the contravariant tensor Bij are said to be conjugate tensors if and only if their product will give us the Kronecker delta. A second order tensor has conjugate if and only if the determinants formed by its components is non-zero. Now, the last thing we look at about tensors is the metric tensors. And suppose we consider two neighboring points. We want to consider two neighboring points in the coordinate system. We can call one point xi and the other one xi plus dxi. So that if this is the point here and this is the point, another point, we can think of the distance between them. And the distance between 2 points, normally when we have 2 points like that, this distance dxi can be expressed in terms of the component here and here, using the Pythagoras theorem. So basically we can, if we know the value here and here, we can always apply the Pythagoras theorem. That is two-dimensional. We can generalize that into higher dimensions. So the distance between these 2 points is given by ds2 is equals to gij, dxi, dxj, where it is assumed that gij are functions of xi, and gij is a metric covariant tensor, that is gij is equals to gji, and the determinant of gij is non-zero. In this case, the space will be said to be a Riemannian space, and Gij, the symmetric covariant tensor of second order, is known as the fundamental tensor or a metric tensor of the Riemannian space. Now, the quadratic form given here in this equation 1.28, the quadratic form given there, we call it a metric. And we can have some examples. In 3 dimensions, the rectangular coordinate system, we have that the distance between 2 points, ds, is given by, this is basically the Pythagoras theorem in 3 dimensions, where we have x, y, we have x, y, z. We have the coordinate system x, y, z, and we can determine the distance between these points as ds squared is equals to dx squared plus dy squared plus dz squared. So that in this case, if we want to replace x with x1, y with x2, and z with x3, so that we write this in general form, then we shall have dx1 squared plus dx2 squared plus dx3 squared. In this case, we think of a 3 by 3 matrix, where we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and then we have dx1 squared, dx2 squared, dx3 squared. So in this case, the coefficients here, you see now this is the matrix G, I, this matrix here, this one. So that when we write Gij, this is should be Gij, not Gii. So when we write G11, this will be 1. G22 is the value here, which is 2, and G33 is 1. Sorry, G22 is 1, and G33 is also 1. But whenever I is not equals to J, yeah, like G12 we get 0, G13 is 0, G21 is 0, G23 is 0, G31 and G32 are all 0. So we can write that Gii is equals to 1 and Gij is 0. Gii are the elements in the principal diagonal. Gij is are the off-diagonal elements. Now, if we go to the cylindrical coordinates, remember the cylinder. When we think of a cylinder, the base is a circle of radius r. So when we think of an element here, this angle is delta theta, and this is r, length. The length of an arc here is usually given by r times delta theta. So we shall be thinking of moving in the, when we go to the cylinder, we are thinking of a cylinder. Let me draw the cylinder down here. The cylinder has a base which is circular. When you superimpose this to a coordinate system here, you have the, let me draw it well. You have the center here. From the center, you have the z-axis. Then you have the y-axis. And then you have the x. So in this case, whenever you want to move, you start from somewhere here, you move from the center, not just anywhere, from the center, you move along the x-axis up to, you don't have to move along the x-axis. You start from the center, you move towards the surface along the direction R, and then you move up. This direction is along the radius, so it is R. Then you may move up along the z-axis. So you'll be partitioning the cylinder. This is Z. And then you move loud here. You move in this direction along the surface, which is represented by theta. So the length of an arc here, when you take a slice of this, I want to draw another line there, then up like that, so that we partition, we do a slice of the cylinder. This angle here will be delta theta. So the length of an arc, the length of the arc here will be R delta theta. Then when you are moving up, you are moving along the z-axis. So you'll be talking about the length dz, a small length dz. When you move along the radius, then you can think of the small length delta r, so that you have the quantities delta r, r delta theta, and dz. So in this case, these are the components. These are the components in the r-axis direction, in the theta-axis direction, and in the z-axis direction. Because here we have the directions, 3 directions, r, theta, and z from the cylinder. So that dl squared will be dr squared plus r d theta squared plus dz squared. And if we want to generalize this so that we represent r by x1, theta by x2, and z by x3, then we write dx1 squared plus d plus x. See that we have r, x1, then dx2 squared plus dx3 squared. So we can write this one as dx1 squared plus x1 squared dx2 squared plus dx3 squared. And you can see now that when we write g11, we'll get a value of 1, the coefficient here. G22 is x1 squared, and G33 is 1. Then for any other value, Gij we get 0. So here we have the matrix Gij being equals to, we have 1, 0, 0, 0, xi squared, then 0, 0, 0, 1. So the matrix is of that form. If we go to the spherical coordinates, then the components are usually, when we think of a sphere now, we don't have z. Now we have, because the sphere does not have a straight line. All the sides are curved, or the surface is curved everywhere. So in this case, we have dr squared plus r d theta squared plus r sin theta squared d phi squared. And if we were to write the matrix, then we will have the first component here is the coefficient of dx1 here, which is 1. The next one is x1 squared, just like we have here. And the last one here is x1 sine of x squared. sine of x2 squared. And this is x1, not xi. This was supposed to be 1. This is 1, not I. This is x1 squared. So in this case, g11 for the for the spherical coordinates, we have I g11 is equals to 1. G22 is equals to x1 squared. G33 is x1 sine of x2 squared. And gij is 0 whenever I is not equals to j. Now we say that ds squared is positive definite if it is positive for all values of the coefficients of the differentials dxi, where dxi are not all 0. So we look at the conjugate metric tensors next. So next we look at the conjugate metric